So today's review lecturer is Axel Kleinschmidt from the Max-Planck-Institut of Gravitationphysik in Rome, and Axel will be talking about consistent truncations and equals to gravity. Thanks.
Oh, so we're okay. Well, thank you very much for the introduction and for the invitations to speak here.
Which is fine.
There's actually this talk. I was struggling a bit to see how it fits into the theme of the conference, but I was asked to talk about consistent truncations by the organizers, so following their vision.
Long one.
So I've already taken the moment to write a few things on the blackboard in case you want to look at some references. The thing that I would like to explain today is, first of all, what is the problem of consistent truncation? Why is it important? This will be sort of a first motivational thing, and then I will try to explain the modern view on how to obtain consistent truncation in a good way. Which is that we use this machinery of the exceptional field theory, which is a particular way of reforming low energy effective action of string theory, where certain symmetry structures, namely exceptional symmetry structures, are made manifest. And in this reformulation of gravity and supergravity theories, you can perform a particular type of reduction called general Schwarz reduction that automatically generates for you consistent truncation. And this sort of approach, to me, was mainly pioneered in the context of exceptional field theory in this paper here by Bohm and something a few years ago. And what I hope to get to, if I manage in view of the time towards the end, is a report on recent work related to D equals 2 supergravity. So this is interesting, particularly for a number of reasons. It hasn't been done before due to technical obstacles related to the symmetry structures that arise in 2 dimensions, which I will also review. And it's also interesting because this is, for example, the arena where you make contacts by holography. You find ADS2 solutions, you make contacts to matrix models of the type of BFS. So you want to find a consistent truncation that captures SO9 invariant. So I hope I will get there at the end, but since this is a review lecture, I will start on the board and go fairly slowly through these things. So please interrupt me at any moment with questions. So the first thing that I probably should at least immediate once is that what is a consistent truncation? So we all know that string theory at low energy goes through supergravity. And if you do this, for example, or you can also do this with M theory, we typically end up with supergravity in 10 dimensions or 11 dimensions, which are of course too many dimensions. So the problem of consistent truncation then is to write this 11 or 10 dimensional manifold as the product, either let's say consistent with my rotation. Let's say the 11 dimensional manifold as some kind of product manifold of a d-dimensional and 11 minus d-dimensional internal manifold. The product would be one. And if you make this kind of compactification, and that's where you assume this is a small manifold. The problem of consistent truncation is now finding configurations of this type. So you find an effective theory on this. Manifold, d-dimension, by truncating certain modes on the internal phase, so certain modes until the 11 minus d. But truncating means just throwing away certain terms in the equations, and the problem of consistent truncation is when is this process actually such that you obtain a solution of the original theory, which is what you want to embed or interpret as some string theory configuration eventually. So the question is this consistent means what it means a solution in d dimensions is also a solution in this case 11 dimensions. So what I want to find is an effective theory in d dimensions. So this will just be a d-dimensional theory, and any solution of that I want to be able to update. If I just talk about one single solution, I mean the problem is a bit uninteresting. I mean, you really want to explore stability of solutions, perturbations, fluctuations, and so on. So you want to have an effective truncated theory in d dimensions where you can then, in the neighborhood of a given point, uplift any configuration in d dimensions to the level. And this is a hard problem, as you can imagine. So this is hard.
And this is beyond just using the zero mode.
Exactly. Exactly. So I mean, the question is, what do you mean with zero mode? So in general, if this is a complicated state, and you will have a complicated harmonic analysis for your analysis. And let's say famously, this is a sphere, for example, not any sphere. You can do an expansion in spherical harmonics and restrict to the lowest mode. It's not always consistent. With very strict restrictions on even if you take like the lowest Fourier modes in this thing, whether this provides a consistent truncation with this different. Other questions? So this is hard because the yes. Uplift. Uplift. Sorry, this was the jargon. So uplift means exactly what I'm writing. What I was describing here in different words, which means that you take a solution in lower dimensions, you can uplift it to a solution to higher. So it's an embedding of a solution that is d-dimensional effective theory into the 11 dimension. Well, I will write in a second. I hope.
You go with it. I mean, given that
so if you do this thing here properly, so you really, I mean, you have to describe what you know or specify with the truncation. So what is the exact truncation process? Which means, for example, saying which modes of the harmonics here you can keep, then you get a unit uplift. Because you really have a one-to-one map, and you start out with fields that depend on all of these coordinates. You do some reordering or rearrangement of the fields before there's certain terms, but then this means that, I mean, the thing that you ended up with the effect of, you know exactly how to put it into configuration. Sure.
Right. Then you're doing from one dimension from the other, completely spectrum of some operators.
So this is ideally what we would like to do. I think kind of the outcome complications actually are never consistent on this side.
If we use the mic for questions, the volume below.
But you can hear me well.
Yeah.
So this is hard because the 11-dimensional equations are highly nonlinear PDEs, of course. So we can't just throw away some terms and obtain a consistent truncation in the central domain. So there are some known examples, which we're already into that. So the first one is, of course, the standard. Let's say it's Hamilton reduction. On, let's say, just a circle or a torus. So, and here, what you do in the consistent truncation is you just put the zero modes in the Fourier expansion. And the question is, why is this consistent? So this is consistent because of group theory. So when you, let's say, you go to the circle example, there's a U1 group action associated with the circle. And the zero Fourier modes are singlets of this U1 group action. So if you restrict completely to one singlet sector, you will never touch the non-zero or non-singlet sector. So this will be consistent. There's no term that you can write down where the non-singlet sectors are triggered by the singlet. And I will give you more details on this in a moment because it will relate to this structure of hidden symmetries and extension.
How about that if I have two non-singlets making a singlet? Would it be this one?
Well, so what you have some equation that you have a singlet, which can be solved by singlets, or as you say, you have non-singlet square. Yeah, this kind of structure is given, but the truncation removes this term. So this is a consistent truncation from that point of view. And what I'm saying is that if you want to write down the equation for a non-singlet, let's say box non-singlet, you cannot write the source that this contains only the singlet. You always have the singlet times non-singlet.
Let's say
So here, if you set it to 0, you set the equation trivially decoupled. So this is why this is consistent. But yeah, but this is a special case for it. This is all about classical. So this is completely in the classical supergravity world here.
the same would be true for areas 4 of that 7.
Coming up. So this was an example for consistent truncation that we were asking. Is that for expansion along this circle? There's a periodic direction, you Fourier expansion in that, and there's a zero mode in this Fourier expansion. Well, Fourier expansion fields to start with. So all the fields that are here, I take it up with coordinates where I single out one in the circle direction. I do a Fourier expansion along that circle, and then in this, then I write the field equations here in the way that I was sketching because along the Fourier expansion, Fourier mode by Fourier mode. Here I can throw away the zero mode in this Fourier expansion. So then other examples are sum. So let me underline this, the sum here reduction. What famously what you can do is something like ADS pi times pi in type 2b. And you can also do something like ADS 4 times 7 in 11 dimensions. And proving that these are actually consistent truncations is extremely hard because they're Fourier enough. And this one was done in the 80s in Nicolai. This one at the nonlinear level was only completed a few years ago. Even though this is sort of at the underlying a lot of ADCP holography from the early days, poster child case, actually proving the consistency in this sense at the nonlinear level was only done about a week using these methods. So, and just to tell you that this is not obviously not always consistent, what is not consistent is, for example, if you go to the ADS S8 in 11 dimensions. So there's a restriction on what we can do in terms of sphere compactification, but any sphere compactification is consistent.
Our ADS 3 cross is 3 cross.
I think with the K3 you get in trouble. But I mean, yeah, if you have products of spheres, I mean, then you have more, and there are more possibilities. So this was just for reducible spheres. I think the K3 would get you into trouble. I think that's consistent. And so these are yeah, so there's early work in the 80s and like quite the linearized level by Warner and write it down. United and Romans, and the more recent thing, this was work of the bit Varela Ciceri. and give you a reference.
There's some.
No,
Something.
no. So there's maybe, I mean, here for the sphere case, for irreducible sphere, let's say, there's some paper like that. Yes, read it. With some mild assumptions that needed the code from but what you will find, I mean, this is very useful spheres, and you find two cases and one more, which is 87 times 4, and the list of the list is, I've given you almost a complete classification. So, and then, I mean, one last example, which is relevant because it connects to what I will say later, is some so-called short-form reduction. So what is the short-form reduction? This is something that with isometries, or maybe isometries, on this compactification when going down. To make this statement slightly more meaningful, you can do this, for example, on that's one again, which is one of the original cases that Sherlock was considered. So normally here we restrict to the zero mode. So let's say the coordinate on the S1 I call phi. And then I have some field, let's say the scalar field phi, which depends on the coordinates x on the other direction and the circle direction, and the normal this is just independent of phi, and the Schwarz reduction twists in this dependent in a very specific way. So it keeps just the circle direction in very simple dependent explanation. Sometimes it keeps a Fourier mode which is different from the zero Fourier mode, but actually n here is not quantized necessarily. It should be. And if you do this thing, then if you do the twist correctly, because of the Lie structure that underlies the Lie1 again here, you can show that this is also a consistent reduction. So this produces deformed or deformation 100% reduction. In particular, this is why I chose the letter, produces masses for field. So why is this important? In the usual kind reduction, we reduce massless fields to massless fields. In this kind of reduction ansatz, you can produce masses from higher dimension. This is like a spontaneous generation of mass terms due to the geometry of the So I think the original way this was set up, it's always used these symmetries often. So this even might be a new group, and then you could use the new symmetries, and then they show that there's consistency. What I will discuss later is a generalization. That's a good question. I haven't thought about it. I would think so, yes. As I said, the original theories will be good, but I think that this should also be possible if you have a discrete or finite assembly to do so. Okay, so this looks like a kind of sporadic list of examples, and as I was advertising recently, the progress made in having a more general or broader view on this problem. This is what I will explain next time. So I want to talk about hidden symmetries, which are symmetries that arise in a non-obvious way from the reduction. Let's first talk about the obvious symmetries. So hidden Caliphate reduction. Let's say you go from 4D to 3D in general relativity. This is something that all of you will have seen, I suppose. Relativity. You're going to write the unlots just for setting the notation. We're going to do some decomposition of the metric. Where the four-dimensional metric is decomposed into the three-dimensional metric, a vector field, and a Billerson field. And the reduced action, so you assume of the zero is the independence of the circle. The truncation condition. That's one that you use here. You get with reduced aspect. By S3 and with more factors like a neutral function. It looks as follows. You get a gravity theory in 3 dimensions with an Einstein-Hilbert term. So I'm going to Einstein frame, which is the reason for this rescaling here. Coupled to scalar field and the Maxwell term, which has a non-trivial coupling to the scalar field as well. So, this is sort of a very standard calculation. What I want to focus on here is the symmetries. So what are the symmetries? And the symmetries will be sent from 4-dimensional diffeomorphism. So, of course, what we have here is magnetic diffeomorphism symmetry. We also get a U1 gauge symmetry for this gauge field. And on top of that, this will be the main problem. We get a global scaling symmetry. Which acts as the phi shift by a constant, let's see. The vector field, I think we want to shift it by the same constant or scale it by the same constant, and the metric doesn't do anything. So you can convince yourself that this is a trivial symmetry of this action because this time is invariant and the scaling here is absorbed in the scale. And this descends from the diffeomorphism by n, which just uses times the circle direction. So I call the circle direction pi again. And you can have a diffeomorphism parameter for the 4-dimensional diffeomorphism parameters that you can linearly on the circle direction. If you go to the formula for diffeomorphisms and the action on the fields in the metric, you will find that it uses these constants. C's. So, this is the guaranteed obvious symmetry that you get from the reduction or from the reduction. You get global symmetry. In some sense, they're associated just with the scalings of the surface, if you do a more general reduction on the torus, you can scale or change the shape of the torus in different ways. You get more symmetry. So for time reduction on the torus Tn, you get Tn. The symmetries of the torus as global 2. So these are not hidden symmetries, they're really just symmetries that you get directly from the ansatz and from the property of the geometry. To get hidden symmetries, you have to work a bit harder. Use this in there.
The is going from the form.
So this so this is a three-dimensional gauge field. This is just the usual. So this, yeah, so the capital indices are for I didn't explain, the capital indices are the four-dimensional ones and the small ones are the three-dimensional ones. So this is three-dimensional, the Biot field strong.
If only on just two to get an SU2 gauge group, that's not going to work.
If you do it on an S2, yeah, you get an SU2 gauge group, which is not going to work. I mean, first, I think, yeah, SO3, I think would have been.
Yeah, SO3.
Yeah, but
that works.
No, that doesn't.
That doesn't work.
Yeah, but it doesn't work. It's not, you can do the calculation, but it's not consistent. You can write on you can get a theory with C2 symmetry in that way, but it does not consistently embed into the higher level. Good. So I'm going to squeeze and in here the hidden part. Non-nullable. And to understand why there are extra symmetries of this section here that you are not seeing when you look at it, let me look at the equation of motion. So the equation of motion for this vector field here take the following form. So there are the ends of e to the minus 2 pi. So we have to throw the p as well, f and n equal to 0. So this is the usual Maxwell equation, except for the coupling to the relevant field that you have to put in. Now, the point is that you can solve this equation locally by introducing a dual field. So I will say that the 1/2 epsilon m and p f and p. This should be equal to e to the 2 pi p and chi. The chi is now a new field that I introduced sort of randomly here. If you substitute this in here, you will see that this vanishes automatically because you get anti-symmetric derivatives. This is why the epsilon is there. This is the dual field. Scalar. And it's also often called the axiom because it has shift symmetries. You can see it has shift chi here by a constant because of the derivative, and this doesn't do anything. So it's a scalar field of axionic type. Whereas the phi here was a electron. So, so here, well, I mean, we've just written down a local solution to the equations. You can actually use this dualization equation here to rewrite the action, which I will do in a moment. Now, in terms of the fields phi and chi, but we already see here that we at least have gained one symmetry in the process. I will show you in a second that we gain more than one symmetry. So let me rewrite the action. So it turns out that more or less you can, this looks a bit illegal, but you can convince yourself that you can do it. What you get is more or less substituting this value for f2 here. Which is always dangerous, putting in equations of motion into the action, but there are ways of making, of justifying it in this case. So if you do this, what you end up with is e to the 2 pi dm chi dm. So now this is a fully equivalent way of writing this holographic reduction from 4 to 3. This step that I was doing now is only possible in 3 dimensions, this dualization. Clearly, if you're in a different number of dimensions, I mean, this dualization will not produce scalar fields but forms. So again, yes, please.
It looks like when you solve the x equation of motion over there,
Yeah.
you're only left with equations of motion for negative part. But when you plug it back in, it looks like I should go for the equation of motion for part.
Exactly, yes. Yeah, so here, if you do this, I mean, you get equations of motion for the metric and the 2 scalar fields.
But in the
which is,
original description of the field strength,
Yeah.
you would have had an equation of motion for metric.
Yeah.
One scalar,
and the
and
vector,
you solve that equation.
and the vector field.
But that's one solved with that answer.
Right, so the equation of motion that you get here for chi will be exactly this, I mean, this equation. So this is the consistency now. So and we exchange the equation of motion by dualization, but here I mean you get the equation of motion as an invisibility condition.
Sorry, you get the same equation of
Well, I mean you put the epsilon in here the same. I mean the equation of motion that you get for chi here will be something like a box chi is I don't know what. So this will be the DM here in for. So if you hit this with another DM, this is the equation. DM of this is 0, so you know the equation of motion for chi is, and this is equal to. Okay, so yeah, so this equation already has 2, so this action you see already has 2 constant shift symmetries and phi. And in pi, if you compensate correctly by phi d. But you can actually rewrite this whole thing here. And everybody here knows hyperbolic geometry, so you have recognized it already. You can rewrite this as a SL2 over SL2 sigma model or cosine model. And the way that this works, for example, is I will introduce some B, which is an element of SL2, so it's split in 2 by 2 matrix. And this B will have transformation properties. So it's the B of X, if you come from coordinates. This is all split wheel. Split wheel. So the coset structure here means that the way that this SL2 element is formed is that the local SL2 gauge symmetry, this is why it's a coset space. At any point you can do local SL2 rotations, and this is local, and this. And it has a global action by the group on the space itself. So I'm not changing field, I'm not yet. Albrecht wouldn't be happy with it. This is all real, something complex. So yeah, so what you need to say? So this is I can write an element B in this way, which has the symmetries. So if I can write down an action, or if I can rewrite this expression here in terms of B with these symmetries, I will automatically have a global SL2 symmetry manifest. So, and we can achieve this by gauge fixing, for example, gauge fixing the SL2. If I write the V in the following way, e to the phi over 2, the phi over 2 times chi, minus pi over 2, and work out the following Mohr-Kaplan type derivative. So I just take this element E that I've written here, which now includes the field pi and chi that we want to connect to. I take this Mohr-Kaplan derivative and decompose it into the Lie algebra SO2 and its orthogonal complement. Then what you can show is that everything that is written here is equal to the trace of GMN times the trace of this and what you can also check from this definition here and these transformations is that E will transform it it's this under the transformation will transform covariantly under the SHSO2, which means that because of the trace here, this is invariant. So this thing here is a scalar SL2 invariant. Which means that I can write this reduced three-dimensional action in a way that has manifest SL2 global SL2 solution. And this is really a hidden symmetry. So it's something when I started doing the calculation, if you don't know about it, you would not necessarily have guessed it, but going through these steps, you can manifestly bring it out. I think the first person who realized this was probably Ehlers in 1957 or something like this. So this goes back a long way. It's not written in this way in his thesis, but it's all the ideas.
So can you trace it back to what was holding the
Right, so very good question. So the key equation is the dualization equation. So here, I mean, you can of course now work out how does this SL2 act on these things, and if I write this in terms of some power, it's A power plus B divided by C power plus C. This is what this is doing. But in terms of these, this is what it does on pi. If you trace it back to the field of the original method, it will be a non-local transformation. Because you have to integrate this to get the transformation of the component in the metric, and it's a non-local transformation in the origin. It's really something that is a bit indirect.
So it's an non-local transformation, but it's a global symmetry in the 4D language. So
But it's only a symmetry after reduction. It's not a symmetry of
right.
Exactly. So there's a conserved charge in 3 dimensions, not in 4.
And that doesn't come upon the charge in 4 dimensions. It's not an integral over charge.
Well, because this is consistent, it's a charge in 4 dimensions for a special class of solutions, namely those that are in isometry.
Oh, I see that.
Yeah. So it's only, and it's a conserved charge for specific 4-dimensional solutions, those with isometries.
So when you say it's a symmetry in 3, you can operate on the fields in 3 dimensions,
Right.
and use it as field configurations.
Yeah.
But this will look indistinguishable in 4.
No, I mean, it also does something to do. So I can act on these fields that appear here in the 3-dimensional language. So I have a transformation in 3 dimensions. Then, because it's a consistent truncation, I can use this formula to say what it does to the 4-dimensional metric. Right. But this is only on the space of 4-dimensional metric that admit this thing with the isomer. Here I didn't write the coordinates, but here I also see the
Symmetry on the solutions of the base with that symmetry.
Exactly. So it's a symmetry of the space.
Yeah,
4-dimensional gravity solution.
And we would note that yes, there is this sort of chart before
Yeah, I think it's fair to say that I certainly wouldn't have been maybe other people would have, but I mean, because this is, as I say, a very indirect way of getting this thing. An analogy that I'd like to look at this point is, hidden like the Kepler problem of quantum mechanics. There's the 1/r potential, which is SO3 symmetry, but also that there's this accidental symmetry, which comes from the Roman lens vector, which is SO3 plus SO3. So you can write down any 1/r to any power with perfect rotational symmetry, but only if you want to take 1/r, you have an extra symmetry. And this is the thing that allows you to actually integrate or solve the Kepler. And here it's a bit like this. This is a very fine-tuned system where something special happens. The question?
It's not associated with translation long diagonal to the
But there's one which comes from
that's only the quantum number again.
yeah, I think that's one. So here you have three conserved charges because the three-dimensional symmetry group, but I think one of them is somehow related to the it's not right on the note, but there's some relation to it. Other questions? Don't think I will get to the Okay, so this was the first instance of hidden symmetry. That's SL2R, which extends the Paul's field in maximal supergravity. And so this is something that goes back to the late 70s, early 80s, when you do maximal supergravity. Of course, you have not only the metric, you have a number of other fields, P-form fields, fermions, and so on. You can do similar calculations. So when you do the reduction from 11D on an N torus, the first thing that you get is the sort of manifest GLN global symmetry. But this in maximal supergravity is extended to an exceptional EN symmetry, which contains the GLN. So it extends the GLN, and here again I will say that I'm using the split real. Pretty confusing. So this only works if you have maximum supergravity. If you work only bosonically, similar question on the bosonic fields. This fixes the value of the Max-Planck constant. So what I mean by this statement here is if you start in 11 dimensions, you write down the metric with freeform with an arbitrary value of the transcendent coupling, you do the reduction. In order to see this enhancement of symmetry, you have to take the right value of the transcendent coupling. At no point you have to use the word supersymmetry of fermions. So normally this is fixed by supersymmetry, but demanding this in also fixed. Which is fine. For example, maybe I will go 7 in 4D and 3A in 3D. And in general, what is EN? So what I mean with EN is the rotation diagram. M. So with EN, I'm even keeping only the nodes up to number n in this diagram. So there are some degenerate cases when you go to low values, you have to be a bit careful what you do when you come to this application point. But there's a well-defined way of making sense of this diagram, and it gives you a sequence of symmetries En, first discovered by covariance analysis. And the GLNs that I was talking about here is basically this subdiagram of the EN diagrams. This is type A, you get an extra torus direction, so you have GLN from the subdiagram. The 1, 2, 3, third node is related to the just a comment here, because somebody was asking about classical or not. So in string theory, what we expect right into the n the integers from the string symmetry group. So this is the usuality by Hohenhausen. And this idea actually is quite powerful, so I could go off in a different direction, which would be more in line with the theme of the conference here, to talk about now automorphic forms related to this discrete higher rank symmetry group. But yeah, let's not go in this direction. We can talk about it afterwards. Good. So this is yes, so here you go to the higher rank automorphic form. So here, the one comment I could have made here is this was largely restricted to at most an 8-dimensional torus. So you only went down to 3 dimensions, and in 3 dimensions you get this nice maximal enhancement, generalizing what I was explaining before. What I want to talk about for the rest of the talk is what happens in 2 dimensions, because new things happen in 2 dimensions. So, well, let's do that. So we do the obvious thing. So we do consider that we do the reduction again to 2 dimensions. So we use some appropriate decomposition now of the 3-dimensional metric. Yes.
Here in every case, we seem to visualize the concept.
Yes, it is clear. You realize everything to as low a degree as possible.
And also you the field which don't go to start.
Yeah, exactly. So I mean, the 3 form, when you do the reduction of the 3 form, you get different rank P forms, and you always realize them, if possible, to lower degree, and only then you see this. You don't know. So the first time, well, let me make a little remark on that since you asked. So I mean, you start with the 11-dimensional 3 form. This is due to so let's say in d dimensions, this is due to d minus 5 form. Yeah, d minus p minus 2. This is correct. So the first time that you can produce a scalar from this free form by dualization, this one is equal to 5. So first scalar. So the first time you use it, if you dualize as much as possible, the first time you can get a scalar from the free form is in 5 dimensions, which by this thing up here means that it should be part of these. And in some sense, this is gratifying because the first time you really get something exceptional going out of the thing is when you see the effect of the extra field in the. Which was just, but you always have to dualize as much as you can to as low rank as good. So we make an ansatz for the three-dimensional metric now, and you'll first try to check this. So this is not a three-dimensional metric. Then there will be some standard of fields that are now called W, just for distinguishing it.
Sorry, another question. Is how to say convoluted operation? So can you say that I don't point the Inverso? So it's not method, but the going to be some method. That's what platform.
Exactly. So, which is exactly what I'm doing now. So I'm starting with the three-dimensional method, which is already the reduced theory, and then I go one more step, so you can do it. Or you can do this with which is what I'm doing.
go to the computer.
I can here and can say that. But it turns out that there's another conserved current we can construct out of the Y. Which has some other conservation quantity, and if you do like that, you go down to conservation equation from this. So here we so we have generating theory. This is a formal series. I mean, you can actually try to that the scalar is Laurent is something rather around infinity or zero. If you invert the really but what equations will I write down for this generation series that relate to my activity? So the equation for the generation series that I can call it will be the following. So you'll look at this like this. Constructed. You will be maybe not fully satisfied. I've just cooked up this equation. I mean, finding that equation, that's also procedure for it, but I've just
Based on the pattern, yeah. Well,
getting. So I've just cooked up this equation, and when I write down this is what you always do in integrable systems. You put that you can also call it very close to standard integrability. The only sort of wrinkle feature here is that you have to make sure that gamma flows basically. So you see from this gamma that's the space condition. So gamma here is just I've introduced a new object into the game. It's a new function. It's a new scalar function. And let me write the equation that will make it easier. Sorry, I'll come.
Write it down. What you presented now, it seems that you start from generating this upscale. Start with the development, multiply the universe. You must have done all the manipulation building the system. Is that possible? Or are we postulating building this?
So the way I presented it, I just postulated this. I postulated this, and in the postulation, I introduced some new object gamma. But you can also do it slightly differently. You can say I write down which is what was done originally. You say, okay, I don't make any assumption about the right-hand side. I just say it has to have certain covariance properties under XL2 and call these coefficients A and B something. And then you demand again this thing here, and then you end up with this form.
No point in what we know. Upstairs, you define the notion with the heads using concept currents.
Yeah.
This is not now what you use for running the system.
No. So I mean, what I use is that I want to have an object that depends on this W that has this limiting point. But I did not use the conservation. I did not use anything about the equations that these things satisfy. So the equations that these things satisfy, for example, this one here, this will drop out of this equation here if you extend it out to first order. And that's why I was saying that if you expand it to first order 1 over W squared, you will get the other equation that I never remember because it's contained in here, but it's algorithm.
So what the equation is this equation plus the equation for what segment?
So yeah, okay. So when I say this thing here, I get what I mean with this. I mean 1 and 2, where this is 1. And 2 is the equation that rho is free field. I'm not, and the equation for sigma I'm not writing because it comes from the Inverso. So this goes on this. I'm just using these two.
So it doesn't fix the independent bubble.
Yeah. Exactly. Very good.
So I understand what you are telling from how you mentioned you are using to
Correct.
but the number of things that you have in the area is finite.
Mhm.
And this is why if I put the terminal in the area, to be somehow find a certain number of components in the area example, which have to be finite.
So indeed, so what do I get from here? So I started out with a system which only has a finite number of scalar fields for the reduction, and here I've suddenly introduced an infinite number of fields. And this infinite number of fields, I mean, most of them are auxiliary, spurious, whatever word you like. So some of them are related to the origin, but most of them are just auxiliary. So they are introduced to make symmetries manifest. But you can always sort of remove them if you want to, and at the end of the day, if this what this is expressing, go back to just the physical field. So here you have the finitely many fields, but the intermediate steps I have extra things to make structures. I wanted to write the solution for gamma to satisfy everybody, and that is something.
An equation which defines gamma.
It's an equation that gamma has to satisfy, and you can so explicitly
So
solve.
I'm saying that. Yeah,
The
not that. The one where gamma is first introduced.
Yeah.
So that defines gamma.
So this is just a certain parameterization of the coefficients in an equation.
Is there a reason why it's chosen in this particular?
Yes, so actually maybe I should do some reference here. So this is the paper that I was mentioning in the very beginning. So this was back to I think 87 or 86. What they did is they put arbitrary coefficients A and B here. So they say whatever we have on the right hand side, it must be expressed in terms of Q, P mu, and the mu of P. And then they work out the integrability condition and demand that we want to get the GR equations. If you demand that, this fixes A and B to be of this form, and then the left with still is this last equation. So I've jumped over this one step, so I've just put in this algebraic part of the problem and to the differential part. So yeah, it looks a bit ad hoc here, but this is, I mean, you can do derive this. It's not something you have to get started on. So we'll see. So actually, we can get a two solution. Quadratic. So the solution is one on the row. Then there's some integration constant. And there's this filter, which I already mentioned. And then these two branches together. That's filter squared. And so it's not too complicated as a solution. And here, I mean, this is the integration constant that you're wondering about, and I can write this integration constant as a function of W. This equation here makes no reference to W whatsoever.
But if you just do the W also.
I could exactly. So the standard choice is to choose this to be W to relate these two integration constants, but this is actually a choice. And we relate it to this Irretorral extra Irretorral symmetry that I was also mentioning, but I don't want to go into that. But here we clearly get an integration constant from this equation. And I can just relate this to W in some way.
What is W?
Rho tilde is the view, so if you take this equation here, you can dualize it. It's a big view.
Okay.
I take the definite, right? The dual view to Rho tilde. Because here you see, and then write it. I can do it here, so I can use this thing. I can write this as d mu of Rho tilde. This is why when you integrate this up Rho tilde. But it's an explicit solution for this gamma and the FDP solutions. You have to choose the branch. And there are, so this gamma is something called the space-time dependent vector parameter. So this is something that is different from when you do integrable systems in two-dimensional field theory, not gravity. You only have one spectral parameter, and here in Franz there are two spectral parameters in play. One is this constant W, and the other one is the space-time dependent, and they're related in this way. When you choose f of W to be W. If this has been a choice, you can make other.
Yeah, but this at the moment, whatever it's done, the extra mileage, I will not call in extra mileage.
So the extra mileage that you get is that somehow the only thing that you want is that this gamma, when you send now gamma to 0, I think. So here we've made certain assumptions about what this generating field is, certainly infinity. And if you know this is a function which is not W but on gamma, which you can also relate to the physical field. So what this extra mileage here that you get out of this is that you can make certain local reparameterizations near the point where you expand. So the infinity of 0.
That depends on your function as W.
Yeah, exactly. So you can. I mean, what you can do is here you can do something like this, but W cubed and so on. So you can make a different parameterization here. If you wanted to, I mean, this is works. And what we have to do is that when you W to 0, I mean, I think you have to start with a. So you can make higher order corrections to this and the extra mileage that you get out of that. is that here these three parameterizations, with the x behind other stuff, they're related to the Inverso transformation. These are the dimorphisms, analytic dimorphisms on the plane, which are related to the Inverso transformation.
But they're related to this y.
Yeah. I mean, here, if you make a look, so here, I mean, I've defined very precise y, but if you relate this to the other generating series, then of course it will be something that is the field.
Sorry,
Well, but then you have to I could write one where it's here all the time again. But then you lose the freedom of making certain diffeomorphisms. I think there is some mileage to be had by keeping this formally separate, but for more practical calculations,
So again, so the requirements they are just like the property of one or linear combination.
So the, I mean, really in a fewer definitions of y, will bring different powers of W, but there's a relation between these two.
But I mean, you have the same limit by using different multiples.
Right. So what you want to ensure is that sort of near the boundaries, if you want, like 0 or infinity, I mean, you have the correct limit to the physical fields, but there are several ways of achieving exactly. Yeah.
There's not equal geometric representation of bubble.
Physical. So it's yeah, I'm not sure that I have a good answer for that one. I mean, this W, as I would say in X, and as I already alluded to, is related somewhat to an affine extension of the symmetry. And of course, there are several algebra acting in this W. So affine extensions are related to loops. So you have some kind of loop group expansion, and you can say maybe this circle from the loop group, maybe this is physical in some way or the other. But I don't think I want to pursue that interpretation. So I would say there's no direct physical.
So there's some relation of this system to, something called anyone for the story.
Well, not at all.
You said the power of W in the definition of Y.
Yeah.
Do you want that because you probably want the terms to be invariant as W goes to infinity, right? I mean, how do you impose that constraint then? I mean, if I absorb a 1 power of W in all the Y's, so you start with Y1, Y2 by W, that is the dot.
No, but so I think this is not what the I mean, you don't want to absorb the W. I mean, you can sort of multiply some of these exponentials together using the exponential.
Oh, I see.
Like I mean, you don't want to get rid of the W. So the W you don't want to absorb in Y. You want to reach. But I have a feeling, sorry, I mean, this for the S of W, this is important. The technical point for the experts, I really want to get. Sorry. Get to the with some other statement, which is wider applicability. And which may come back in Europe. So the thing is now this from this W. So there's so here you can choose plus or minus of the solution as a function of W with this condition. So you can write the generating series either in terms of W or and if you do this, you can check that both and one standpoint of X and 1 over gamma of W based off the linear system. So there's a certain involution that you can apply. So if you have one solution, you can apply a transformation, which automatically produces for you another sum. And
Without one over down, not minus one.
this one of them. This is the Chevrolet evolution of the apparatus. That's the concept in the negative. So, but since you get two always two solutions coming together, you can define something which is M, which is the product of these two solutions. It's a bit like a matrix constructed in a field line, with each definition of field line. A fixed product, or maybe one or row square or something like this. So, but here, as I said, I'm choosing. I think I'm choosing plus in both cases. So I'm not changing the sheet.
Is it in this case just gamma minus?
Yeah, it's good. You can choose one of the other. Yeah, so it's well, but I didn't want to do that. Yeah, you can write this is gamma plus and this is gamma minus without. But the point that the statement that I want to make now is that if you define this product here, this actually turns out to be independent of it. So this thing here, which is called the velocity, is actually constantly active. It only depends on W. And a lot of interest, if I understand correctly, Gabriel will say more about this. It's related to this property here. So this modular matrix. You just give me any constant matrix in SL2, which depends on W. If you can take this matrix and factor it in this way here, with certain prescribed limiting behavior, so you want to say something when gamma goes to 0 or gamma goes to infinity, so you give certain analytic properties here at 0 and infinity for this factorization problem. If you can solve this factorization problem, you automatically get a solution of two-dimensional gravity. So this is really a solution generating technique. I start from any matrix here. If I can factorize it in this way, with the right boundary condition, so the analytic structure, then because this V contains the physical fields, I automatically get a solution to the two-dimension. So solving this Hilbert problem. For finding solutions. Gravity. And we can also mention the word garage in this context. It was the first one to think about this, because when I say 2D gravity here, I mean you can think of this 2D gravity also to four-dimensional gravity, where you have done two reductions. So when you ask the question on the space of solutions to four-dimensional gravity with two Killing vectors, commuting Killing vectors, can I apply some solution generating technique? And the two commuting Killing vectors are equivalent to saying you can do a reduction of the problem to two dimensions. And now it turns out you have a very powerful solution generating technique to construct solutions in the class of four-dimensional gravity with two Killing vectors, like stationary axis dimension. This really is meant, and there are formal arguments that this thing here produces for you all possible solutions of four-dimensional gravity with two commuting Killing vectors, and actually the single orbit of the symmetry, which is this affine symmetry. But from the title, I think this is what you will talk more about, right? For those who are still here. Good. So the focus. The chair is high. So the focus. So in this talk should have been the symmetry. So you get an affine or loop extension. Of this ELAS. So the extension SL2 F is just the set of all G of W, where G is in SL2, and W is it's in the punctured complex plane. Maybe you want this to be neuromorphic or something like this. So there are again technical discussions to be had. So if you assume this is meromorphic, then this is really just a loop of SL2. And the way that this is constructed is that if you take one of these monodromy matrices and you do a transformation by G of W by factoring from both sides, here you will not violate this, and you have a way of generating solutions from solutions using this infinite dimensional symmetry. And just maybe to comment again on the question that you asked. So here really you have an infinite dimensional symmetry, and the role in life for these infinitely many fields is just to share something with this infinite dimensional symmetry to act on. So it just reshuffles these infinitely many fields. At the end, you have to solve this problem and project it into physical field. But it's really these are auxiliary objects for making this structure as transparent as possible. Talking about which, so hopefully made some things transparent. I actually haven't talked about the consistent truncation bit, but I think we should probably stop at this point. It is. So for the diagram, but E9 by definition, so if you have the maximum supergravity, E8, you take the affine extension, this is positive for E9. There's some subtleties here with the central charge and derivation, but I mean this is basically the affine extension of E8 is E9.
No, I find it in the level.
Right, so okay. So here, so E9 is this times the algebraic generator times the group generated by E1 plus 0. So this is the level. So, but maybe what you're asking is, so E9, I mean, this is affine symmetry. If you look at highest grade representation, so this you classify them by levels. It's the representation of level K equal to 1, K equal to 2, and so on. So this K is the central charge. So there's also a central charge K that measures which level you're in. And what I was describing here, this is represented trivially, but I mean, you cannot. This also plays a role in the bigger scheme. So the bigger scheme of things is that here, what I didn't get to talk about is you can rewrite now this theory with this big symmetry in a way where the symmetry is also manifest. It's not manifest in this action here. Because this doesn't have all the fields, you can try to cook up some two-dimensional system, or actually exceptional field theory system where the symmetry is manifest. If you do this, you see that you have to work in a representation, or it's useful to work in a representation of E9 where this K is equal to 1. So you use, in some sense, affine at level 1 this thing, and this is related to this gauged deformation of this theory here, embedding tensor and all these things, so then you really need to use K. I mean, I'm happy to explain more, but it's a long way to explain. Other questions?
At some point, you mentioned Inverso. I don't know. So from the point you can get the result in this thing, it's the option for this thing of
The Sugawara construction of the
but you need to impose some constraint. It's not obligatory, it's not that much.
So here, I mean, so when I have these things here, I can also define generators which are just one d by dw, so differential operators acting on this function here, and this is like neuromorphic and this pre-delta neuromorphism. So these generators I can use to act on these functions and resolve the space of these functions, and then I can ask the question is, are these also symmetries of the system, and we can actually make them symmetries.
And from there you use a lot of the
This is the these are the various generators. And these, I mean, as you can see from the, I mean, these are vector fields in W, and these, if you take these now and look at the group generated by this, these are differomorphisms in W, so they send W to S of W. So to connect to the previous discussion. I mean, these generate reparameterizations.
And but all of this is on chart. So you have
Perfect. Yeah, it should. So all these symmetries, since I was using the equations of motion, this is on an on-chart symmetry. Perfect. Yeah, I should have emphasized this more. Well, so you can interpret some of these as non-local, and not all of these come from diffeos. So first of all, you have to be on this subspace where you have two commuting isometries, and then some of these are diffeos, and some of these are non-local transformations.
Then, you, whatever,
so there's a, so this thing itself is a superfluid. I'm not sure, and there's a terminal version of this, which is really, I mean, this was only goes on it, where you expand this equation here, but it doesn't make it superfluid.
There's something more in now to reduce one more dimension.
Excellent. How much time do you have? So it's very suggestive, and it was already suggested by Bernard Julien in the 80s, that if you go one more step, you should see, instead of P9, you should see P10, which is a hyperbolic algebra. And people have, including me, but most of the other people have tried to make this manifest, like Bernard Julien, really see this E10 symmetry in one dimension, but nobody has succeeded. And the one problem here is that what was important for getting the denial symmetry was using the equations of motion and the realization. When you go to one dimensions, realization becomes hard. And then that's why you can't cook up these extra fields on which you can cook them. So this is the simple reason, I think, why it's not obvious to make the dream come true, and people have other perspectives on this question now, but it's not proven that we can exist in dimensions. And if you want to ask, if you go one more step, there are also these conjectures by people West about E11 and related to supergravity, and this his view is there should be E11, but not in 0 dimensions, but somewhere actually in 11 dimensions, but also there you have to make certain gymnastics to get meaning to that statement. It's also, I would say, not